In the previous lesson, a bandpass filter kept a useful middle band around resonance. Now we invert that idea. A band reject filter, also called a notch filter when it is narrow, passes low frequencies, passes high frequencies, and removes a band around one center frequency. The shape is easy to recognize. The gain is high on the left, drops around the center, and comes back on the right. The deepest point is the notch. The two -3 decibel points mark the reject band edges. So the same landmarks return: center frequency, lower edge, upper edge, and bandwidth. One passive way to make a notch is to put a resistor in series with the signal, then connect a series LC branch from the output node to ground. Away from resonance, that branch has high impedance, so the output node is not strongly loaded. At resonance, the LC branch becomes almost a short to ground, so the output voltage falls. The center frequency comes from the same resonance condition as before. The angular center frequency is 1 over square root of LC, and the Hertz form is 1 over 2 pi square root of LC. The difference is not the center equation. The difference is where we take the output and how the resonant branch is connected. On the band reject magnitude plot, the curve starts near 0 decibels, dives near the center frequency, then returns near 0 decibels. The ideal notch would reach -infinity decibels, but real components have loss, so the notch has a finite floor. A practical filter is judged by both notch depth and reject bandwidth. The reject bandwidth is ω2 minus ω1. A narrow notch removes a very specific interference tone, like hum or a switching spur. A wider reject band removes more neighboring content. That can be useful, but it can also damage signals close to the unwanted frequency. Now compare the passive examples. An RC low pass keeps slow changes. An RC high pass blocks slow changes. A series RLC band pass keeps the middle band. An LC notch rejects the middle band. They all come from the same voltage divide idea plus frequency-dependent impedance. Here is a quick notch design. If L is 10 millihenries and C is 100 nanofarads, the center frequency is about 5.03 kilohertz. Place the series LC branch as a shunt at the output node and use the surrounding resistance to control damping. For a sharp and deep notch, source resistance, load resistance, and component losses must be included. The biggest passive filter trap is forgetting the source and the load. A filter is not floating in space. It is a voltage divider connected between stages. A load can move the cutoff, reduce the notch depth, or change the effective Q. Component tolerance shifts the center frequency as well. A practical recipe is this. First, decide what you want to pass and what you want to reject. Second, choose the passive topology. RC for one-sided filters, RLC or LC for middle band behavior. Third, compute the landmark frequency. Fourth, check loading, loss, and tolerance before trusting the curve. Summary. A band reject filter passes both sides and removes the middle. A narrow band reject filter is a notch filter. A series LC shunt branch gives a clean passive notch example. The same resonance formula sets the center, while loading and losses decide how deep and how wide the rejection becomes.